A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, U, V, W, X, Y, and Z. You may have noticed that I skipped the letter T in the alphabet. That's because I'm shaped like the letter T. Not only is tea a letter, it's also a beverage that's commonly enjoyed all over the world. Some people will sweeten their tea with milk, sugar, or honey. Honey comes from bees. Bees usually live in colonies, and a honeybee colony is where honey comes from. A colony is usually led by the queen bee. The queen is the mother of most, if not all, bees in the beehive. If you like biology, bees are a really interesting insect to study. A cool thing about a beehive is that drone bees, or male bees, are born from unfertilized eggs. That means that they only carry one type of allele at each chromosomal position because they are haploid. In simple terms, male bees don't need a dad. On the other hand, female bees need both a mother and a father to be born. Now this is pretty interesting because if you chart out a bee's family tree, it looks kind of weird.
Here we have a drone or male bee, and male bees only need one parent, and it's usually the queen or a female, but females need two parents, one male, one female. That male only needs one female parent, but the female needs two parents. And as you can see, you can draw a little family tree for multiple generations going up the bee's tree. So here I've got another grouping, but it's getting too small to write the letters, so I'm just kind of improvising. If I label however many bees there are per generation, you'll see a weird pattern that evolves. 1, 1, 2, 3, 5, and 8.
This pattern is known as the Fibonacci Sequence. This sequence is pretty cool because it appears in a lot of places, like bees. The sequence has been around for a while, supposedly originating in India, where it was described by Indian mathematicians. There's a cool way to draw a spiral using the Fibonacci number. This sequence appears in strange places in nature. No matter what kind of flower you look at, chances are it has a petal count of a Fibonacci number. For famous examples include the lily, which has 3 petals, buttercups, which have 5, and the daisies 34, and so on. Within the sequence, there is a ratio that I will talk about later on, and that ratio appears in the way that petals and leaves are spaced apart from each other. Strange, right? Seems supernatural, although there's actually no magic here. Flowers, seeds, and whatever else grow in this way because it's the most efficient way to pack a number of things in a small space. To learn more about Fibonacci numbers in nature, I would strongly suggest watching the video in the description. Now, remember that ratio that I was talking about? It's called the golden ratio, which is defined as the ratio of 2 numbers that is the same as the ratio between the sum of 2 numbers and the larger of the 2. In simple terms, it's like 21 and 13. 21 divided by 13 is pretty close to 34, their sum, divided by 21, the bigger of the 2 numbers. You can get really close to the golden ratio as you go up the Fibonacci sequence because it naturally involves numbers and their sums. Here's the actual golden ratio, at least the first few decimals, 1.61803398875, and so on. Now, try it yourself. Divide up 2 Fibonacci numbers, and the higher you go in the sequence, the closer they get to that number. But wait, how do we know what the number is if the Fibonacci sequence goes to infinity? There's no way for us to ratio the biggest Fibonacci numbers because it never ends. Intuitively, we would just take a really big Fibonacci number and do the ratio like that and get close to the golden ratio, but that's not very accurate. Instead, we can actually just put in variables for the things that we don't know and then do some math. The equation goes like this. A plus B over B is equal to A over B, which is equal to phi, which is the Greek letter they assigned for the ratio. Now, if we just go ahead and split that fraction up, we get A over A plus B over A is equal to phi. Well, alright, let's go ahead and, A over A would be 1, and then B over A is the reciprocal of A over B, which is 1 over phi, using the step beforehand. So now we have 1 plus 1 over phi is equal to phi. So to get everything onto one side, we can multiply by phi to get it out of the denominator, and then you have phi plus 1 is equal to phi squared. You'll notice that you have a simple quadratic equation, which then you just use the quadratic formula and you'll get 2 solutions. Now, one of those solutions is negative, but it's actually quite interesting, and we'll get back to that in a second. The other solution is the 1.6. I think it's really cool how it all works out like that. I was talking about leaves earlier, and plants and leaves grow with... There's a car driving by, but I will not stop. Leaves are cool because bees pollinate flowers, and flowers sometimes have leaves, and plants and stuff, but whatever.
If you're a plant, your goal is to space your leaves in a way that there's no overlap, but you want to have as many leaves as possible. So in order to do this, you need to space your leaves at a certain angle that is a fraction of a circle. So it actually turns out that the most optimal way to do this is to go 1/5 of a circle, or 360 degrees divided by phi, which is about 222-ish degrees. That's pretty weird, isn't it? That this golden ratio appears in leaves. But the reason why it's there is because it's the best possible way to create a leaf pattern where every leaf can go in a circle and not overlap another one, and they can pack a lot of leaves in there really tight, and they can all get adequate exposure to sunlight. And so just over time, this ratio of how spaced out the leaves are becomes like a natural thing.
Again, a quick Google search can tell you all sorts of things about the golden ratio, but I can't talk forever about it. Now, moving on, say we took the Fibonacci numbers and squared all of them. You'll get a sequence that looks like this: 1, 1, 4, 9, 25, 64, 169, and so on. Although these numbers seem unrelated, we can do the same technique with the numbers and see something really cool. 1 plus 1 is equal to 2. 1 plus 4 is equal to 5. 4 plus 9 is equal to 13. And you'll see that the pattern is just skipping the Fibonacci numbers, and it continues forever. Now, let's say we add up each square number consecutively. So going back to that square list, say we have 1 plus 1, which is 2, or 1 plus 1 plus 4, which is 6, 1 plus 1 plus 4 plus 9 is 15, 1 plus 1 plus 4 plus 9 plus 25 is 40, and so on. Well, these numbers make their own list, and they're actually multiples of the original sequence. 2 times 1 is 2, 2 times 3 is 6, 3 times 5 is 15, and so on. And as you can see, within this one sequence of numbers, you can get a lot of different sequences just by playing around with it. I would encourage you to try and play around with this and find some cool sequence, or maybe even make your own sequence and then call it your sequence instead of the Fibonacci sequence. Now, I'm running out of time here, so I would really just encourage you to research this sequence and other sequences similar, and you can find really cool about its application to the real world as well as in mathematics. And as always, thanks for watching.